Hello. Today we discuss limit theorems. These statements are very important tools to help us determine the limit of a sequence. First, we start with the definition. A sequence is said to be bounded if there is some number capital M in the set of all real numbers such that the absolute value of Xn is smaller than or equal to M for all natural number n. The idea of the definition is that we construct we can construct an interval uh, from minus m to m. This is a definite interval. Then every a, a sequence is bounded if every element of that sequence is within this interval. That is, x1 is somewhere inside the interval, x2 is somewhere inside the interval, x1000 is also somewhere inside the interval, xn for any n is somewhere inside the interval. We have a definite interval, and every element of the sequence is within this interval. In that case, the sequence is said to be bounded. Now, an immediate consequence is that a conversion sequence is bounded. The idea of the proof here is based on the definition of conversion. Remember, a sequence is said to converge to some number if almost all elements in this sequence must be inside a small neighborhood of that number, except for finitely many terms. So in this problem, in the proof of this theorem, we pick a value for epsilon, let's say epsilon equal 1, and we consider the one neighborhood around the limit of this sequence. Then almost all elements of the sequence must be inside this one neighborhood. There might be a few elements that are not inside the neighborhood, but we only have finally many of them. Then we can use the triangle inequality to show that these these other elements must be um, must be bounded by a certain number depending on the limit of the sequence and the absolute value of finitely many terms outside of that one neighborhood. A consequence is that the sequence xn equal n is divergent. How do we prove it? This is another example of proof by contradiction. So assume that the sequence here is convergent. Then immediately by the previous theorem, this sequence is bounded, which is a contradiction to the Archimedean. property we learned from the previous chapter. That's why this sequence, that's why the assumption must not be true. That's why the sequence must be divergent. If it's not convergent, then it is divergent. That's the definition of divergent. And that is the end of the proof. Now we're going to have several statements which tells us how the limit interacts with properties of the real numbers. The first theorem is about the limit and algebraic properties. Let the let's consider sequence xn and the limit of xn equal to x, and consider another sequence yn, the limit of yn equal to y. Then we can take the limit of the summation of these two sequences, the limit of xn plus yn. The theorem says that this is exactly equal to the limit of xn plus the limit of yn, which equal to x plus y. That is the limit operation and algebraic operation can be interchanged with each other. You can take the addition first and the limit, which is equivalent to taking the limit first and then do the addition. Then you have similar statement for the difference between two sequences. The limit of xn minus yn is exactly equal to x minus y. And the statement here follow in a very similar manner. The limit of xn times yn, this is x times y. The limit of c times y xn is equal to c times x. The limit of xn divided by yn, when the limit of yn is not equal to 0, then this is equal to x divided by y. So in general, limit is said to be compatible with algebraic properties of the real numbers. That is, you can interchange the operation of taking limit and algebraic operation. Here is an example. The limit of the ratio 2n plus 1 divided by n, this equal to the limit of the summation 2n divided by n plus 1 over n. Now 2n divided by n, that is simplified to 2. The limit of 1 over n is well known, is equal to 0. We discussed about it in the previous lecture. That's why, applying the theorem above, we immediately arrive at the conclusion that the limit here must be equal to the limit of 2 plus the limit of 1 over n, which is 2 plus 0, which is equal to 2. Similarly, the limit is compatible with order properties. So here, when you have the limit of xn equal to x and xn greater than 0, then x here is greater than equal to 0. If the limit of xn equal to x, the limit of yn equal to y, and xn is smaller than equal to yn, then immediately x must be smaller than equal to y. Also, if a is smaller than equal to x and smaller than equal to b, then a here is smaller than equal to the limit of x and is smaller than equal to b. That is the inequality can be passed to the limit. The next theorem is a very important theorem which allows us to determine the limit of several sequences. It says the following. Let's say xn smaller than equal to yn smaller than equal to zn. So here we have three different sequences. Now suppose that the limit of the smallest sequence xn equal to the limit of the largest sequence vn equal to some number l, then the conclusion here is that the limit of the one in the middle yn is also equal to l as well. So that's why it's called the squeezing theorem. Y here is the sequence yn is squeezed by the sequences xn and vn, and you can visualize it as follow. Suppose you have xn smaller than equal to yn smaller than equal to zn. Now the larger sequence converges into some number l. The smaller sequence also converges into some number l. That's why the one in the middle yn must converge to this number l as well. Here is an example of how to use that theorem. Let's consider the sequence yn equal to psi of n divided by n. We would like to determine the limit of this sequence when n approaches infinity. The intuition is that when n is large, the number psi n over n is small. Remember, psi n is bounded by the parameters of the psi function and can become enlarged as you wish. The psi n, because this is a psi function, it must be between -1 and 1. That's why the intuition is that when n is large, the denominator is dominating. The numerator is too small in comparison with the denominator. To make the argument progress, we proceed as follows. -1 smaller than equal to psi n smaller than equal to 1. Therefore, we have that minus of 1 over n is smaller than equal to psi n over n and smaller than 1 over n. Now, by the squeeze theorem stated above, for xn equal -1 over n, yn equals psi n over n, and vn equal 1 over n, and the observation that the limit of -1 over n equal to the limit of 1 over n and equal to 0. This is again an application of the Archimedean property. By the conclusion of the theorem, the limit of psi n over n must be equal to 0 as well. Another application of the theorem is the following corollary. If the limit of the absolute value of xn equal to 0, then the limit of this sequence xn is also equal to 0. Again, it follows by the same squeezing argument as we saw earlier. Another corollary is that if the limit of xn equal to x, then the limit of the absolute value of xn equal to x. Please note that the converse is not true. Here we have an example that the limit of the absolute value of the sequence equal to 1, but the limit of this sequence doesn't exist. So this statement goes in only one direction. Another theorem is about the compatibility of limit and the square root. Remember, the square root operation follows from the completeness property that we discussed in the previous chapter. In order to define the square root of 2, we take the supremum of the set of all numbers such that square of that number is smaller than or equal to 2. The supremum of that number is exactly the square root of 2. So that's why the square root operation follows exactly from the completeness property. Here the theorem says that the limit operation is also compatible with the square root operation. If the limit of the sequence xn equal to x, and xn here is non-negative, then the limit of the square root of xn is exactly equal to the square root of x. Another theorem which is also very useful is called the ratio test. Say that let x equal to xn be a sequence. If xn greater than 0 and the limit of the ratio xn plus 1 divided by xn equal to L for some number L smaller than 1, then the limit of xn here must be equal to 0. So the limit here comes from a consideration of the ratio of consecutive terms in a sequence. That's why it's called a ratio test. Here is an example of how we apply this theorem. Let's consider the sequence xn equal to a to the n for some number a between 0 and 1. We would like to find the limit of xn. The proof goes as follows. We consider the ratio xn plus 1 divided by xn. This is exactly equal to a to the n plus 1 divided by a to the n. By simplification, we arrive at a, which by the assumption of the problem, the number a here is between 0 and 1. Therefore, the limit of this ratio is equal to a, which is a number between 0 and 1 by the ratio test, because this sequence satisfies all the assumptions of the ratio test. The conclusion is applicable. That's why the limit of xn here is equal to 0.